for the field trip. Yay. Finally hit the magic double digit.
Finally hit the magic 2.
Congratulations.
So whatever we did yesterday is working.
Good. Yeah, there were several other students who I'm trying to
Some
help
from
them
your 201 and
get
a few other people.
excused from their other classes they're in.
Yeah.
And writing emails on behalf of students.
Yeah.
Okay, so we have a guest here today. Alicia, you want to introduce yourself?
Hi, I'm Canicia. I was an ERM student last year. I graduated from the ERM program, and I worked with Al. I was a student worker, and it was a lot of fun. I got to do a lot of different things, projects, international projects with them. So if you guys are ever interested in like gaining more experience or actually doing hands-on material, I definitely recommend you talk to Al. Yeah.
Sweet. Okay, Alex, so good.
Welcome. We wish you could be here for all of our classes, but did you ever take this one?
I didn't, no.
Okay.
This is a new one.
Hopefully you'll learn a few new things, always adding to the knowledge.
Yeah, it's great.
And let's see if there's any other announcements. So I sent a whole bunch of emails around about trying to get the teams paired up.
Yeah.
And I think everybody knows about Zihao Chen. Everybody know who Zihao Chen is?
Yep.
Former ERM club president, and he's a student worker working with me. So he's helping me to try to put together for the last 4 classes. I did the quick math on this, and it looks like we're going to need 4 classes to do the student presentations, and it's mostly because we have a lot of independence, which really is not what I was hoping for. I was hoping that most of the students would form teams, because it really is inefficient to have a whole bunch of independent presentations. So I'm going to have to cut back on the allowable time, especially for the people who did not form teams. So Zihao and I are going to be hammering out the schedule for presentations during the last 4 class meetings. And unless you've already told me which specific day you want, you will be randomly or arbitrarily assigned a day.
I'll volunteer for the last day. We'll end on a good note.
You know, especially if you could send me an email to remind me
Okay.
on that. At any rate, there's still an opportunity to form teams. If anybody can do that, I would appreciate that. Then that's about it for the announcements as far as I can think of. Luke, you already made the announcement about the field trip. Thursday evening, there will be a guest speaker who is an ERM alumni, one of our early graduates who owns his own business over in Texas. He's an inventor and is basically making and selling products that are helping to clean up the environment. I think specifically radioactive waste and minimizing radioactive waste generation. That's going to be over at the Union, one of the Cooley ballrooms on Thursday evening, probably about 6. I will send the announcement around. Dr. Olson just gave me something a few minutes ago. I haven't posted it yet.
I'll post it to the club.
Yeah, thank you, so we can get the word out. For those of you who are in the 502 class, we'll have a short evening on Thursday so that we can go over and watch the speaker. And it's all part of the Polytechnic campus 20-year anniversary celebration. This campus used to be a military base, the Williams Air Force Base. Everybody refers to it as Willie. And it is a Superfund site, a national priority Superfund site. So I'm planning on using this Superfund site as a case study next time we meet on Thursday this week. And let's see, the following week, is that the first week of November already? I guess it is. So Dr. Burge will be coming back. I think he's going to do both Tuesday and Thursday on more water transport stuff. And then I think we end up with the student presentations all the rest of the semester after that. I wanted to spend more time on remedial action, but You'll see, we'll get through what you really need to know going into it, I think, at the end of Thursday. Okay, so last time we were meeting, we were talking about the distinction between transmissivity and hydraulic conductivity and the diagram that's showing up there, whereas hydraulic conductivity is classic Darcy's law, and it's limited to just the one by one section of the aquifer and how much volume or flow you're getting through that. But transmissivity is a term expressing the entire depth of an aquifer, not just a unit of 1 meter or 1 foot, which is what Darcy's law predicts and calculates. So the equation for transmissivity includes that depth factor in an aquifer. Once again, these are very simplified extrapolations and based on ideal conditions, which we don't usually see in nature. So you need to always take this with a drop of water, a grain of sand, as we go through groundwater hydrology, because there's a lot of leaps of faith that you have to make. So the rest of this lecture is on trying to figure out flow direction for groundwater flow direction. Once again, in one of these idealized situations, the first slide up here talks about how you construct a flow net, and it's pretty much something that we can all read together, but you need a minimum of 3 observation points. This is a PDF, so I can't draw on the thing, unfortunately. Sorry. Need 3 piezometers or monitor wells, and you need to have a surveyor who will go out there and survey the elevations, and then using a measuring tape or other groundwater measurement device that's common for groundwater monitor wells, you drop that into each one of the 3 monitor wells and determine what the top of the water is in each of those 3 wells. Then you draw the map. You'll see the map here coming up, and try to determine the proportionate lengths showing the differences in elevation between all the wells, until you finally, at the bottom of this paragraph, you join the points of equal height on the lines of your drawing, which means you've got the same height of the depth to groundwater across this map that you're making, and you select the contour interval, which is appropriate for that overall variation in the water levels. So it's much like drawing a topographical map. If anybody's familiar with topographical maps that are used for hiking, you're going to have contour lines at the end of it, showing the relative elevations on your map. This slide here, we can continue to read. It you have to have a scale on your map. You're going to see the map in a minute with a north arrow and a pretty accurate scale in terms of how many meters are in an inch on your map, so to speak. And a lot of this is intuitive, but there are some mathematical equations which you will be seeing here to help you more accurately draw the contours on the map. So once you have a contour map that's complete, then you can draw flow lines for the groundwater flow by dividing the contour lines into equal lengths and creating flow lines that are drawn at right angles to the contour. And this will all be displayed graphically here on the slides. And the idea is to try to continue to work on drilling more wells if necessary at your site until you're confident that you have an accurate groundwater flow for your site. So if we assume we're starting out with only 3 piezometers or 3 monitor wells, And they can be drilled only to the depth of groundwater to save money at this stage. If you just are looking for the initial determination of groundwater flow direction, if you plan on using these same monitor wells for years and years and years of groundwater monitoring, which is often required by the regulatory agency to verify that the contamination is cleaned up and it's not coming back, sometimes the regulatory agency will not close out a site, a remedial action site, for 5-10 years or more. For the NPL site, nobody knows when it will ever be closed. A lot of our national priority list sites around the country have been going on for 30 years, 40 years. No end in sight for some of these really large cleanups. But if it's a really small cleanup, you might be able to get by with shallower groundwater monitor wells. Keep in mind that from earlier lectures, groundwater rises and falls with seasons. Groundwater rises and falls with large flow events that are happening from a rainy period, or if there's a boundary condition like a water or a lake nearby, and that rises or falls based on flows. It's going to put more recharge into your aquifer, and the aquifer will rebound and bounce back up in the monitor well. So you need to understand your site so you know how deep to make the monitor well. But the deeper you go, the more cost it's going to be. At any rate, in this example, the case study, we're just starting out with 3 wells. And the numbers are on the chart there with, you can see well number 1 having the highest elevation, and 2 is middle one, and and then 3 is the lowest elevation with respect to the ground surface. You need to have a surveyor to come in to make sure that the top of each groundwater monitor well is accurately determined. You don't need a surveyor to actually drop the measuring tape down the bore to hit the groundwater, but you do need a surveyor to get accurate tops for each of the wells, ground surface for each of the wells. So this site, you can see the groundwater is not far down, 26 meters, less than 100 feet. That's it for that slide. So the idea is to have a benchmark also. So the surveyor is going to identify a benchmark in the area. They typically are going to look on a topographical map for a metal plate that they call a benchmark. And the nearest one will be where they do their surveying to find the really exact elevation for where you're putting in these wells, and they're supposed to be measured to 1/100th of a foot accuracy. That's why you need a surveyor. It has to be pretty accurate. Oftentimes the levels are given in feet above sea level. The surveyor will also give you the distance between each of these wells. The idea here is to take the middle well, which is well 2 in this case, in terms of its elevation, and then try to figure out the flow direction based on dividing these things into proportional lengths. So if well number 1 gives you a difference between the top of the groundwater of 26, if this distance between 1 and 2, I've got this wrong. If well 1 to well 2, well 1 minus well 2 gives you the difference in the top of the groundwater of 26.28 that you see on here to 26 point, Well, I got this wrong on my notes. 6.2, so you have that difference, and you have the top of the groundwater in the middle of the well and the top of the groundwater in the well 2. You can start plugging in the numbers to the equation to determine which one is where the likely point of groundwater flow would be. You're looking for an equipotential line that's along the vector between 1 and 3. So you know that. I can't draw on this, can I? Try to get to this PowerPoint.
Yeah, and then you just,
Just need a blank slide.
yeah, you just start the slideshow.
Yeah, they're all blank.
All right, so we have the 3-point triangle here. Well, 1, well, 2, and this one is going to be the middle, so 26.2. This one's 26.08. And 6.28. So you know that in general, the groundwater is going to be flowing somewhat in that direction. You want to try to be more accurate than this. You're estimating the differences between each of these, and it looks like this one is maybe about a third closer to the distance than this one, because this one has a greater difference between 26.28. It's 0.2 difference all the way down here. This one is only, what, 0.08 for that distance. So it's going to be about a third of the way down. The right angle would be here to bisect this, but if you're going to try to find the equipotential line for the equal groundwater level in this well in comparison to this well, it's likely to be along that length of the transect, about a third of the way down. So you still don't know exactly which way the groundwater is flowing, but you can start extrapolating by drawing a right angle vector to the line coming off the middle well, that it's flowing in that general direction. I got to go back to my other thing.
Let's just click escape.
Where is it?
On Firefox.
Okay. So this slide gives you the formula to help you draw the proportionate distances between the 3 wells there. And
But X isn't on that in that formula anywhere.
it says to draw a line between wells 1 and 3 and where the water is. This is not an X versus Y formula. You're trying to determine the distance. Do I have an X on this? No X.
Next to what? No, go. Never mind. We're trying to find. If you scroll down more, it doesn't match up at all with the thing on figure 4 or figure 3.
All right. Dr. Burge actually skipped this slide when he presented it because he's not expecting you to actually do this equation in a test. You're trying to get the point that is what they call equidistance at point A here. I can't draw this.
Right, but isn't that what's in figure 4, and the equation in figure 4, the 3-point problem in figure 4 doesn't match the formula on that page?
I don't think I've got to figure 4. This is figure 2.
Yes, but I'm sorry,
Just the one you're talking about?
yes.
Oh, well, you're jumping way ahead. Okay.
Like, if that's how you solve for the point A, I don't understand what in the thing in the equation you've shown me indicates where point A is.
Okay, so this distance is in the wrong direction.
Like, which of those variables has anything to do with point A? That's what I don't
Center.
understand.
Okay, so this distance is supposed to be 200 meters between 1 and 3,
Yes.
and that's what you saw for 200 in that equation on
Yeah, that's why.
figure 4.
You plug in y, distance y is 200 meters, right?
Y, there it is. Yeah, distance y, you're getting ahead here.
Yes, but okay, I'm sorry. I don't understand what in that equation is supposed to have anything to do with point A.
So the distance between 1 and 3 is 200, and you're trying to find out what is this distance.
Right. Isn't that what that equation is supposed to be for?
Then, yes, that's what the
And I don't understand
equation is.
where in that the x is.
So you're taking these are elevations here. The 26.28
Yes,
is
I know. In that equation, it's obvious.
well,
for
one-
students, but in the one the one up further, it doesn't look like that equation at all. It doesn't have any x's in it. The h values on the top are different. Do you see that one has one x and one y? The one further up has 2 y's.
Are you talking about this equation here?
Yes.
Oh, okay.
Aren't they supposed to be the same equation with just the right numbers plugged in?
I don't really know. Dr. Burge did not even explain that slide when he showed it. He just skipped it.
Well, I don't understand anything about any of this.
So you end up with a distance of being 80 meters. I think these are all in meters for this length right here between well 1 and what they call the equipotential line. It's calculating a proportionate distance.
Yes, I understand that, but what is the formula for it? Because
You just make a triangle with it and just say that the distance between the two would be 0.8 on one side, and then that 26.2, and then you just solve for x.
But that formula isn't laid out anywhere. I don't understand what the formula on the top slide is supposed to be if it's not the formula for finding x. I don't understand any of this. None of this makes sense.
All right. Well, you're not going to be asked to solve this problem on a
I know
test.
what I'm not going to be asked, but I haven't learned. I'm sorry. I need to take a break. I'm sorry.
Okay, so that if you've got confidence based on the measurements, and once again using the surveyor's marks, that this is the equipotential point, point A, between well 1 and well 3, you draw a right angle to the equipotential line right here, and you see that the groundwater flow direction is heading down here. This is the general groundwater flow direction. Okay. So what we need to do next is decide whether or not we need more wells to be put in here. So if well 1 is near the point of release, then you're obviously going to have the highest concentrations. And I need to try to find a. Can I show both of these at the same time, Kyle? A blank screen?
With the Y instead of
we'll be able
X.
to
Just a typo. It's the same equation.
Okay.
We don't
So
need to
this
know the
is-
equation. Do what? We don't really need to know the equation because we're not solving.
No, but I mean, even if you go through and solve, it's
It's the same thing.
We have our equipotential line right about here.
and head heights between 1 and 2 and 2 and 3, and then the only distance you don't know is
We drew a vector,
the equal,
groundwater flow direction.
and
Is
then
that-
based on the distance between wells.
Finding the
1
side for a missing triangle, like just use the c squared, b squared, all that stuff.
You're not even doing that. You just
How do I go back to this thing without?
y is a given measurement based on
You just put in the head heights for each of the.
and then the distance between 1 and 3, and you just solve for x. That's literally it. And then you use that to draw the
No.
90-degree line to determine which way.
All right, so I was on this slide, right?
That's literally it.
Okay, so you see the flow direction has been drawn in here, but you still don't know whether or not you found all the contamination. You don't know where the limit of the contamination is. So you're using this map to help you figure out not only the flow direction, but also whether or not you need to install any more wells to find out the limit of the contamination. Let's assume that well 1 is near the point of release. And so it's probably not going, well 3 is probably not going to be the most ideal location for the end of the contour map that you want to draw, especially if it's still having contamination showing up in it. So if we go back to this drawing, and let's say that monitor well has a contaminant level of let's say 20 parts per billion. And down here at monitor well 3, you're running at around 10 parts per billion. And then over here at monitor well 2, it's showing 0. That was a clean well, right? You still haven't found the farthest extent of the contamination with monitor well 3. You have a pretty good idea of where you need to put your next well to chase the plume because you've determined the groundwater flow direction in a much more accurate way after applying the proportionate lengths here and drawing a right angle vector to the equipotential line. And so you install another monitor well, let's say monitor well number 4, right about here, because you know that this is the down gradient, and it comes out at, let's say about 5 parts per billion. That is still not clean. ADEQ wants you to show 0, or the regulatory agency wants you to show where the plume ends. So you have to keep on installing a monitor well. So now you're up to monitor well 5. And that one finally shows not detect, or below the limit of detection, 0 parts per billion, or less than the limit of detection. So now you can start drawing the contour intervals on here. So your 20 part per billion contour line is probably pretty close to the point of release, and your 10 part per billion contour line is all the way down to that well, and somewhere in between here and there you can draw your 5 parts per billion contour line. And then somewhere in here, it's going to drop down to 0. And by putting the contour lines on the map that you originally drew using the surveyed monitor wells, you can present this to DEQ. Now, DEQ is going to want you to also supplement your map and the description of the map with other information like the hydraulic conductivity, the transmissivity, the velocity of the water, and we've gone through in previous lectures how you can do those calculations using aquifer tests, pump tests, and then calculating using Darcy's law and the equations for transmissivity. You can get a pretty good idea how long it's going to take the contamination to get down to monitor well 5, if ever. And the proposal to the regulatory agency might be to immediately install a remedial action project near the point of contamination so that you start shrinking the plume back away from monitor well 5. And that can be then used to convince the regulatory agency to approve your remedial action plan. They're probably still going to want you to continue monitoring all these wells for years to come to determine whether or not your remedial action back up around monitor well 1 is working or not. Is it actually stopping the plume? That's all for that one. Does it make sense? It does? Okay. Questions? Now, do we have any online students?
Yes, we do.
Here we're-
Projects.
We're going to go to this other slideshow that I had up before if I can figure out how to do this.
So just click on that one again, and then you just click on the tab at the top.
Had a remedial action slide here. A remedial action
Should be the one right next to it.
doesn't say remedial actions. I don't know where it is. It's not showing remedial actions. I'll have to open it again. It looks like it disappeared.
Thanks.
Okay. So we're going to start the discussion of what remedial actions are very common all around the world and the United States. And we're not going to get through this whole thing today, but we'll get through a few slides, and we'll finish up the rest of it, and we'll go into the discussion about the case study here at Williams on Thursday. Okay, this is so traditional remedial actions are things like air stripping, soil vapor extraction, dig and haul. You might hear those kind of terms being used. And then you may or may not be required to do a risk assessment according to the remedial action legal authority that is being used to oversee your project. With a national contingency plan driven remedial action under the Superfund law, risk assessments are almost always required for something like that. And there's different levels or tiers of risk assessments that can get real expensive and long term. But for a really small cleanup site where ADEQ or the regulatory agency, usually a state regulatory agency, has already published a cleanup level, they've gone through a risk assessment process for establishing how clean is clean, how safe is safe for contaminants remaining in the soil and for contaminants in the groundwater. Those numbers are usually different. You just look up those published numbers and you don't have to do a risk assessment for that site if you're agreeing to clean it up to those published cleanup standards, right? If it's something that's under the, like I say, sewer fund, CERCLA, they're going to be requiring a lot more risk assessment, site-specific risk assessment, and it's usually driven by the most significant contaminant there, the contaminant that has the highest toxicity. You might have 5 or 6 different chemicals that you're dealing with, but the contaminant that has the highest toxicity to people will be the one that drives the cleanup. You're going to have to clean that highest risk contaminant up to a so-called safe level. EPA generally looks for risk assessment numbers that fall between the range of 1 to the -4, you know, 1 in 10,000, 100,000, 100,000 cancer risk to 1 in a million cancer risk, depending on what the land use is going to be for, whether it's industrial, commercial, or residential, or a school or something like that. And especially if it's a carcinogen, then they're going to look for a more stringent cleanup down to 1 in a million if it's a residential site. So the risk assessments are going to vary depending on the regulatory authority and the law that's the regulatory agency and the law that's guiding it. The next one on the slide here is monitored natural attenuation, and that is a term that we use to refer to a site that probably can be allowed to go on its own if you're keeping track of it and making sure the contaminants are not migrating off site by using your monitor well network, and that there's some natural biodegradation going on or other forms of natural attenuation such as adsorption and partitioning that we've talked about before, then it can be approved by the regulatory agency to just let it sit there for years and years and years and attenuate on its own. So those are typically the kinds of remedial outcomes that we're looking for. Okay, so this slide talks about the different soils that you might be trying to clean up with the top one. If the contamination is in soils only, then that is something that's a lot easier and less expensive than when it gets into the groundwater. And then the contaminated sites that have made, or the contaminants have made it to the groundwater may or may not be documented to be due to your particular site. It could be contaminants that migrated from off-site somewhere else from somebody else's disposal, upgrading miles and miles away. That's what we have all through downtown Phoenix. There's a plume of contaminated groundwater that goes for probably about 100 miles across the entire valley, from 52nd Street all the way out to Tolleson. It's many miles. And some of those properties where the contaminated groundwater is underneath had nothing to do with the contaminants that were found in that groundwater. And the soil could be sampled beneath that site during a phase 2 site assessment and shown to be clean. And so they would not be liable for having to clean up that contaminated groundwater under their site. It's only the ones that are so-called responsible parties under CERCLA. So you may be involved in your careers with dealing with contaminated groundwater sites where it's not necessarily the fault of the property owner. And then if you've got a more complicated site, it has both contaminated soil and groundwater. The regulatory classification for the type of authority here is typically RCRA, TSCA, CERCLA, and then state regulatory agency. TSCA is usually PCB, Toxic Substances Control Act. the different kinds of contaminants at remedial action sites, organic, inorganic, that's misspelled. We already talked about the terms DNAPLs and LNAPLs, and so the density of the contaminant will depend on where you're likely to find it at your site, vertically, whether it's all the way down to the top of the bedrock, at the bottom of the aquifer, if it's a dense substance like TCE, or if it's a lighter substance like diesel or gasoline, it'll be floating on the top of the groundwater. That'd be a light, non-aqueous phase liquid. And then depending on the contaminant solubility, that was also described in an earlier lecture as volatility. It may lend itself more or less to things like air sparging, air stripping, and different kinds of remedial technologies that take advantage of pump and treat and different kinds of pump and treat systems, which we will be talking about. The octanol water partitioning coefficient, KOW, we know that if you've got organic materials below, it's likely to, especially organics, the non-polar organics are likely to partition onto those in the water and also on the soil particles. And then biodegradation, if you're fortunate, you've got a family of bugs down there that will help accelerate the attenuation and the decomposition of whatever the contaminant is, especially organic materials. Adsorption is where we're hoping that the contaminants get stuck onto the inorganics and adsorbed on there rather than partitioning. So here's some of the most common techniques that you'll encounter. Pump and treat. That's an expression that's used for a lot of things because everybody knows what pump is. Pump the groundwater out, but then what do you do to treat it? There are a lot of different things we can do to treat it, which we're going to talk about here today and Thursday. Vapor extraction is where you're intentionally injecting air underground to try to get especially volatile organic compounds to come out of the soil and be extracted through vacuum pumps through a treatment system at the surface. Air sparging is something that is similar to that, also where you're injecting air in underground. You're really trying to move the VOCs back from the soil vado zone to the ground surface. Those are vado zones. Vapor extraction and air sparging are vado zone or soil cleanup techniques. Bioreactors, this is usually at the surface. It can be in situ, which means in place under the ground where you're injecting nutrients and possibly more of a type of bacteria that that really likes the contaminants, likes to eat the contaminants that you're trying to clean up. You can find a different species of bacteria in references to what works best. There's a website I'm going to show you in a minute here called ClueIn, which has a lot of case studies, and there's examples of different species of bacteria that you can pick. But a surface bioreactor might be something as simple as a 55-gallon drum or a series of 55-gallon drums where you're putting the contaminated water, in most cases, or the contaminated soil in there and adding nutrients and possibly heating them up to temperatures that will cause the microorganisms to reproduce more rapidly and do the biodegradation faster. For in situ chemical type treatment, the slide shows both oxidation and reduction chemical reactions that you can try to drive. And a lot of times the organic compounds, especially the chlorinated ones, are more successfully treated with reduction chemical reactions. And probably for metals, inorganics, the most common example of a reduction type of remediation process would be reducing hexavalent chromium to trivalent chromium. There's also permeable reactive barriers here where a geotextile is treated with chemicals that are likely to cause these reactions to go one way or the other, and you bury that in an area where you expect the contaminated groundwater to be flowing across. I haven't heard of that being used much at all here in Arizona. Solidification is another one on the list here, and that's where you're trying to reduce the mobility of the contaminant. You want to, everybody knows what the TCLP test is, right? Toxicity characteristics leaching procedure test of RCRA. So you're going to try to keep those contaminants from moving by solidifying them in concrete or cement type of mixtures that can be injected underground, or you can dig the stuff up and mix it up, rebury it if the regulatory agency lets you do that, or even treat it and haul it off to a solid waste landfill if the regulatory agency lets you do that, provided that you've demonstrated it passes the TCLP test. It's no longer a hazardous waste. It's also typically very expensive and used on metals, cadmium, lead, chromium, that kind of stuff, in smaller sites. Solvent extraction is another pump and treat technology where you're trying to move the contaminants from one solution to another. We'll have slides coming up on that on Thursday. Thermal treatment is where you're using a thermal oxidizer or a catalytic oxidizer. You're trying to raise the temperature to make the reactions go that break down the chemicals. And typically, if it's volatile, you'll end up with the need to get an air permit from the regulatory agency that requires air quality protection. So we'll talk more about each of those as we go through the remedial action stuff. Okay, ClueIn is a really good website to check out. It's has all kinds of articles and case studies. See if I can surf to that. We have another. So it's a .org, but EPA actually is funding it. You can see there's lots of places to click on here, and we'll be taking a look more on this. So you get technologies on remediation. I'm not sure how well you can read that from the back of the room. Can I make this any bigger without messing it up?
Okay.
Different kinds of contaminants. You see a lot of the popular ones, common ones that we talk about. They're on that drop-down list under contaminants. Issues. Oh, they've got brownfields. I think I might have. Yeah, that's the top. What happens if you end up with a fractured rock type of situation? Rain remediation, which means stuff that is more environmentally friendly. Mining site issues, dry cleaner sites. Those are very common. Wood treating. Then here's strategies and initiatives. Optimizing site cleanups. Some of these things they appear to be duplicates. You can also look for products, and vendors, research and development here, all kinds of training opportunities, documents where you can find more case studies. At any rate, this is a good place to look, especially for your presentations, if you're going to do a presentation on remediation. I know a lot of students will probably do that. So why am I not seeing that slideshow that I wanted? It's called something different, okay. One reason or another. We've talked a lot about this already, so I'm not going to spend much time on it. But you know that the federal cleanups are usually NPL or TSCA, Toxic Substances Control Act. And at the state level, we all have to worry about getting our well permits. If you're going to be drilling groundwater permits. In our state, it's the Arizona Department of Water Resources. And then they all have some form of notification that's required, even if it's just a voluntary cleanup action that you need to do. You can't just go out there and start digging and putting in monitor wells. At the county level, it's usually air pollution control permits of one kind or another, but some of the states have sole jurisdiction over air pollution control. So depending on which state you're working in, or which area of the state you're working in Maricopa County, it's Maricopa County Air Quality Department. In Mojave County, Arizona, it's Arizona Department of Environmental Quality, that where you would have to go to get your air permit. And that'll vary from one county to another in the state of Arizona, and similar things may happen around the United States. For cities, it's typically things like planning and zoning and building type permits, where you need to have compliance or demonstrate compliance with the Uniform Plumbing Code, Uniform Electrical Code. Remember, you're going to be installing something like a soil vapor extraction system or a pump and treat system. There's going to be a lot of electricity in use. There's going to be plumbing, etc. So the city is going to want to oversee that. They'll probably come out and inspect the site while it's being constructed and give a green card, a green sticker that says that it passed the inspection, and then you may not see the city again the rest of the time. Then you're just dealing with the regulatory agency that's overseeing the cleanup itself. How clean is clean, Another thing you might run into at the city government level is their brownfields programs. Many of the cities have applied to EPA for brownfields grants, which allow for the abandoned properties, sites that don't have a legitimate owner anymore. Sometimes the city even took it over because the property owner failed to pay taxes and they skipped town. And so there's a lot of contaminated sites, especially in inner cities, that have no responsible party to clean them up, and the EPA has a funding source called brownfields that provides money to the cities, and they can also hire your consulting company to do the project. So at the federal level, there's the brownfields programs, and that trickles down to the cities and the counties. At the state level, it's mostly underground storage tanks. That's the biggest fund for remedial action projects in most states. And that's also dwindling as the years go by. We did have an attempt to rejuvenate that, but the last time I looked into our state's underground storage tank program, that it's still far less money than it was when it was originally launched decades ago. 20 years ago. So the money for cleanups has been federal, state, and other external funding sources has been getting lesser and lesser over the years go by, with more reliance on the responsible parties. to clean these things up. Okay, so activated carbon is a really great substance to use for many remedial action projects, especially those involving volatile organic compounds. And we usually find it in the form of GAC, or granular activated carbon. You buy the stuff by the 55-gallon drum. It can be used to treat air that's contaminated with the volatile organic compounds. For example, the air coming out of the stack of a salt vapor extraction system or a air stripper tower. We're going to see slides about that coming up. Or the contaminated water itself. And then pump and treat, you can just run the water that you're pumping out of the ground if it's a very small flow, especially for things like investigative derived waste flows. You're not going to be pumping for months and months and dealing with thousands and thousands of gallons, but more in the nature of hundreds to the low thousands of gallons. You can get by with just a few 55-gallon drums of granular activated carbon to treat that investigative derived wastewater. But if it's going to be a bigger cleanup project that's going to go for a long time, then you'll need huge tanks of GAC, and that can be very, very expensive because one of the problems with GAC down here at the bottom is it becomes spent after a period of time. It no longer can take on the organics, whether it's through partitioning or adsorption, and they end up becoming useless. You're not removing the contaminant after they get their available pore spaces get filled up with the contaminant you're removing. So it has to be rejuvenated or regenerated or disposed, and typically the either way is very expensive. If it's regenerated, you would heat it up to get the VOCs to come off of the GAC and run the vapors through a still and recover the organics as a liquid. The liquid may have recycling potential or would be classified as a hazardous waste. And then that would be a much smaller volume of hazardous waste to get rid of, rather than an entire 55-gallon drum of GAC. So if you chose to just have the entire 55-gallon drum shipped off as hazardous waste, it's probably going to be $800 to $1,000 for that. But there are services out there that will regenerate your GAC, and you can use the stuff over and over again. It still costs money to either way you look at it. Vapor extraction, once again, if you're running the vapors that have been pulled from the ground through a GAC column, then that's the media that's going through there is air, and it eventually gets the pore spaces you can see get clogged up with contaminants and are unable to absorb or partition much more. So you have to constantly test the effluent from the discharge side of a GAC unit to make sure you're not violating the air permit that you get. Typically, you get an air permit. And that's another cost that has to be factored in to it, right? Air stripping, best for volatile organic compounds. It also can be done with groundwater being pumped out and run through an air stripper tower. And there's vapors are either directly discharged, which is hardly ever the case because usually there's a regulatory agency, an air quality regulatory agency that will require you to do some kind of treatment. If it's a low contaminant site that concentrations going through there are below the thresholds for triggering an air permit, then you might be able to get by without having to get an air permit. But most of the time you'll end up having to install either a GAC or a thermal treatment device to treat those vapors coming off the air stripper. So here's what they look like, cross section of it. It's a tower, essentially, that's enclosed, so you're capturing all of the water and the vapors here, and it's not getting out into the environment in an uncontrolled way. So you're spraying the contaminated water in at the top here. And it's coming through a packing material, which is usually some kind of a styrofoam or plastic material. A lot of times you see plastic balls in these things. And at the same time that the water is cascading down through the packing material, you have a strong current of air. This is just air from the atmosphere being pumped in at the bottom and blowing upwards through the stack of packing material. And, you know, it's removing the VOCs from the water and into the vapor phase, coming out the top of the tank here and over to your treatment, which is typically the thermal oxidizer, catalytic oxidizer, or a granular activated carbon column. So down at the bottom, you've got water that should have most of the VOCs removed from it. Here, you're going to once again encounter the need to get a permit from a city, probably what we call an industrial wastewater pretreatment permit. So your discharge to a city sewer has to be permitted first. It also could be injected back into the groundwater, or it could be used for irrigation water, you know, gray water type applications, depending on what the local regulatory authority is going to allow you to do with that water. I think I did tell this class the story about the city of Scottsdale where they were actually putting it back into the drinking water. Do you remember that story? Yeah, I did tell that story here. And so that's pretty risky. And if you're going to do that, you're going to need to have redundancy in your system. You'll have to have several of these things, and you'll have to have real-time monitoring devices to show that there's that the water that's going into the city drinking water system meets the MCLs, meets the maximum contaminant levels all the time. And you know, that's because of failures of the past where it's been shown that contaminated water did make its way into the drinking water systems where this was re-injected back into a drinking water system. So you have to be really careful with that, and I personally would not recommend that.
Al,
Too risky.
what contaminants were the ones involved?
Scottsdale?
Yeah.
Mostly TCE. So they have trichloroethylene, but along with trichloroethylene, you're always going to find its breakdown products, you know, degradation products, because it does degrade usually in reducing conditions to things like DCE and vinyl chloride. And vinyl chloride is really toxic. It's a known class A human carcinogen. So all of that was or potentially could have been in the drinking water people were drinking in Scottsdale because of the failures of the pump and treat system that went on there. As far as I know, this is what they call the North Indian Band Wash Superfund site. The pump and treat plant is still running and it's still putting the treated water back into the city of Scottsdale water system, but they've added redundancies and they've added this real-time monitoring of it. And of course, all the people who were responsible for operating it are gone. Yeah, this was quite a few years ago when the flaws happened. Did I answer the question?
Yeah.
Okay, so next slide here talks about different bioremediation ideas. and you can try your bioremediation in the soil, or you can try the bioremediation in the groundwater itself. You can try to do this in situ, or you can extract and try to treat it at the surface. Of course, that's more money. So the pump and treat would be, pull out the groundwater that's contaminated, run it through a series of bioreactors, and then out the end you end up with an effluent that hopefully can be discharged to a city sewer, meeting the regulatory agency requirements, right? And then in situ is pretty tricky because now you have to really know a lot about the aquifer characteristics that we've been talking about most of the semester. What are the conditions underneath? Are there clay lenses? Are there silt lenses? Is there anisotropy? Is it more homogeneous? Are there faults, boundary conditions, those kinds of things? And you've got to be able to find out where the chemicals or the nutrients you're putting underground are going to wind up at and follow them. So that can be pretty tricky. See, we have a question from one of our students who's online.
Yes.
What was that?
Did you say that? Oh, sorry. Did you say that pump and treat is more expensive or in situ?
Every site's different, but I think an in situ would probably be less expensive if you can get the regulatory agency to allow you to do it. And you're going to have a lot of follow up to it to watch what's happening. So that can add to the cost. But pump and treat, that means you're extracting stuff, and there's all kinds of costs associated with that. The electricity and the spent GAC canisters that could end up being classified as hazardous waste, and your O&M cost for the pump and treat equipment, because there's a lot of moving parts. You're either forcing air or forcing water to go one way or another under pressure. And so, yeah, you have to do the math on all these. They call it a feasibility study. So you look at all the different feasible remedial action alternatives, and list the pros and cons and the cost for each, and make a decision on what's going to be the best for your situation. Let's say if your client wants a clean bill of health from the regulatory agency ASAP, then the more expensive pump and treat system is probably the way to go, because those take a shorter period of time. Whereas an in situ thing, it's more likely to be approved under a monitored natural attenuation type of scenario, where the responsible party is going to maintain responsibility for decades, maybe 100 years. That's essentially what we've got going on here at the Williams Air Force Base. So the U.S. government has no intention of disposing of this property, or relinquishing themselves of liability. They've taken on the liability, and they have agreed in signed legally binding agreements with the EPA to practice monitored natural attenuation here for who knows how long, a century or more. That's what they signed themselves up for. But if you're a private property owner, that's not going to cut it. You want a clean bill of health from the regulatory agency ASAP, so you can sell your property or use it for other things. So I would say in situ is probably going to be generally cheaper, but very much longer term. Okay, so injection, I think we're going to run out of time here. I'll come back to this next time we meet. You can attempt to oxidize or attempt to reduce. And You typically try the reducing agents for things like hexavalent chromium or chlorinated hydrocarbons. Nutrients they are very successful for a wide range of organics, but not inorganics. Microbes, the same thing. So if you've got a site that's contaminated with inorganics, especially metals, then you're probably not going to be doing bioremediation. And then natural microbes, that's a lot easier to get approved by the regulatory agency because everybody fears the GMOs, right? Genetically modified organisms, the engineered organisms, that have their DNA messed with. And there's this fear, that there could be the killer tomato created, some new monster that was with a lot of unintended consequences. So it's best to try to find naturally occurring microorganisms at that site and grow them out in laboratory culture conditions and enhance their numbers, augment their numbers, and then re-inject them using the same organisms that were there, placed there by Mother Nature, you found and dug up, and can show the regulatory agency that you're not introducing some exotic organism there. On the other hand, there are products that have been approved by the EPA, especially for oil cleanups, that have exotic organisms in there that may be totally different from what's on that site. And you go get a jug of one of those things that are approved by EPA, I guess that can be used too. Population living around there might not like it. So we're not going to go to any more slides here today. Any last minute comments, questions before we break for the day? How about the online students? Take home message from all this is every site is different. There was nothing else? Okay. See everybody on Thursday, right? Yeah. I asked you something. Okay.